Hi, I just want to apologize again for all the emails. I know you're getting a ton of things from me, so I hope it gets better once we get going with this. Like I said, I'm having some problems in Angel, but hopefully everything will work out and we'll get all the little kinks ironed out in the first week. We're moving on to section 1.2 after we've already had the introduction, which was in section 1.1. 1.2 is about sample spaces and events. And a sample space is just a collection of everything that could possibly happen when you run an experiment. So before getting ahead of myself, here are 4 keywords in probability. We have to have an experiment. So an experiment is something that can be repeated an infinite number of times, and you know what's going to happen. You know the set of outcomes that could happen prior to running the experiment. So rolling a die, shooting a free throw, flipping a coin. When you roll a die, you know that you could get a 1, 2, 3, 4, 5, 6. You don't know which will happen, but you know all possible outcomes. Sample points are some of the possible outcomes from the experiment. The sample space is actually a set, and it's just the collection of all possible outcomes or all the possible sample points when you do run an experiment. And a lot of people don't denote the sample space as a set, but it really is a set. In my 2 examples up here, the experiment A was rolling a die and recording the outcome, and example B was shooting 10 free throws and counting the number you make. Sample points for rolling a die could be 6, 4, 1, or 2, or 3. Sample points for shooting 10 free throws and counting how many you make could be 0, 1, 2, 3, actually anything from 0 to 10. So you can see here in the sample spaces, I just listed all the possible outcomes. An event is a subset of the sample space. So an event out of rolling a die could be rolling an even number, and that's just a subset 2, 4, 6 of your sample space. An event could be rolling a prime number out of your as part of your experiment. As an event for shooting free throws could be you make at least half of the free throws, which is 5, 6, 7, 8, 9, 10. So again, an event is just like a subset of the sample space, and it's a collection maybe of sample outcomes that can occur when you do run the experiment. And now lots of laws and properties and definitions. So this is a little bit of a dry section. Definition: if an outcome in an experiment belongs to an event E, then we say the event E has occurred. Keep the current comment, but ask me again, keep the comment. Yes, let's not show this again. So for example, if I roll a die and a 2 occurs, I can say the event E of getting an even has occurred. So as long as, let's say this is an event, again, getting an even, if I roll a die and a 3 occurs, I would say the event has not occurred because I didn't get an even. So again, let's use rolling a die, and event A here's outcome is even. Oh, I guess I already did it. So if we get a 4, we would say event A has occurred. Okay, so we need a few definitions for the next few pages. And so I'm just going to define these right here and then do an example. So a subset, E is a subset of F, and this is the notation we use. If whenever E occurs, then F occurs. E is part of F. Equality: if E is a subset of F and F is a subset of E, we say they're equal. And certainty is if an outcome is inevitable. So for example, the sample space is inevitable when you run an experiment. Certainly something in the sample space will occur. I mean, I'm sure one of those events will occur because you've listed everything possible. So here are 5 events, and then these are just some true or false question. So let A, again, the sample space is you go to the gym and you shoot 10 free throws. So let A be the event of making at least two of them. B is the event of making, so at least two of them would be 2, 3, 4, all the way to 10. Okay, this is event A. Event B is making exactly 5, so 5 is in there. Event C be the event of making between 2 and 10 inclusive, so 2, 3, all the way up to 10. The event D is making an even number, so 0, 2, 4, 6, 8, and 10. And event E is making none or one or more, so 0, 1, all the way up to 10, or actually E is just the sample space. So let's say A is a subset of B. A is a subset of B. This is false. B is a subset of A, but A is not a subset of B. B is a subset of C. B is a subset of C. Yes, B is contained in C, so B is true. A is a subset of D. Here's A and here's D. No, there are elements in A that aren't in D, for example, 3. So this is false. D, A and C are equal. Here's A and here's C, and yes, they're equal. This is a true statement. In E, event E is certain. Yes, when I run the experiment of going to the gym and shooting 10 free throws, I will make 0 or 1 or more than 1. So this is true. Okay, so there was a nice example. And a little bit of notation. So this is the symbol for intersection. So if I have an event E intersecting F, I want all the outcomes that are in E and in F. So by picture, it's just this little portion in the center is the intersection of E and F. I don't like the book's notation. They actually just write EF. They don't put the intersection symbol in there, but that to them is intersection. Union, that's an OR. This is an OR symbol. That means you have to be in E or in F, or you could be in both. A lot of people sometimes exclude the intersection, but if you're in E or F, you could be in E, or you could be in F, or you could be in both of them. That really means you're in at least one of them. Okay, so here's another example. And all these examples I will give solutions to. Trying to find my cursor now. It's okay, it's way over here. So here's some examples. This is perhaps a strange event. A sub k has the outcomes k up to k squared in it for k equals 1, 2, 3. So for example, this is just A3. Let me write, what is A2? A sub 2 is equal to 2, 3, 4. It starts at 2 and goes up to 2 squared. A sub 4 is equal to 4, 5, and it goes up to 16. So for example, A sub 2 union A sub 4 is the union, so this would be 2, 3, 4, all the way up to 16. A sub 2 intersect A sub 4. The only person, I shouldn't say person, number they have in common is 4, so this would be the set 4. And is A2 a subset of A4? No, it actually isn't. And then these are just for any abstract K, any general K, some rules. So otherwise this is going to get too long, so I'll go ahead and leave those. Those will be on when I post answers, they'll be there. So E complement is everybody that's still in the sample space S, but is not in E. So E complement, everybody here is outside of E, this is outside of E, this is outside of E. So E complement everything outside of E, but still in the sample space S. E minus F is E occurs but F does not occur. So E minus F is just this little piece right here without F. Mutually exclusive, we say two events E and F they're empty if the two don't intersect at all. So here is an example of E intersect F being empty. We would say E and F are mutually exclusive. Or you might hear somebody say they're disjoint. Okay. Let's just do a couple more examples. Roll a six-sided die once, let A be the outcome, less than 5. Actually, this is a pretty nice example. I would spend the time going through this if I were you, just listing these different events. And then down here, I'll ask what's B complement, are these mutually exclusive? So again, I'll have all the answers to these in the solutions that I'll post in another day or so, but I think it's good just to practice to go through them. There are tons of facts about sets, events, complements of events, so I just listed some important ones here. A complement is A. If I complement A complement, I get A back. If I union A and its complement, I get the entire sample space back. If I intersect A and its complement, I get the empty set. Here's some commutative laws for events, associative laws, distributive laws. De Morgan's law is a very nice, I think, law that comes into play occasionally when you want to prove maybe A union B complement, and maybe that might be hard to find. It might be easier to look at as A complement intersect B complement. This is just saying this is equality. The left-hand side and the right-hand side are both the same expression, except sometimes maybe it's easier to look at it as the left hand or as the right hand. Somehow I just skipped a bunch of pages. I'm not sure how I did that. So I'm going to do a proof of example 4, but I'm going to do that in another example because this proof is a little bit long, and if you haven't taken 275, then an element-wise proof will be new to you. So this might be your the first time you ever see a proof as an element-wise proof. Down here also I did a bunch of examples. Some of them are from the textbook. I listed experiments, and then I've asked you to go ahead and fill in the sample space. So if we were in class, at the end of class, I would give people time to work on this. So I would make sure you feel comfortable with those. Here's an exercise from the text down there, so you can see what some text problems look like. I'm having a hard time finding that. Okay, so here's one from the text. This is an easier way. So there's one from the text. Here's another one I just made up. And here's a bonus. So again, I kind of made this bonus soon. I would say as long as you can send it to me by Thursday. You're supposed to write out the sample space for single births in a hospital into 2 girls are born consecutively. So the first element in your sample space would just be girl, girl. This fulfills that. The parents keep having single births until 2 girls are born consecutively. The only way to have 3 births is to have boy, girl, girl, right? That ends with 2 consecutive girls. Let me see. We could do for 4. We can certainly do boy, boy, girl, girl. But we could have also had girl, boy, girl, girl. So what I'm asking is to write out enough of these, and you should see a pattern occur. The sample space actually it does follow interesting pattern. You might even see here there's only one with 2 elements. There's only one with 3 elements. And there's 2 with 4 elements, and I can tell you there's going to be 3 with 5 elements. And so this sequence here might look familiar to you. So I think I'm going to cut it there. I'll go back and do the proof and then hit a little bit of 1-3. And I hope you're still doing well.